Second practice problem associated with sample problem 4-3. So here we go. Write the noble gas notation for a gold atom. Oh, okay, I think this is going to be fairly easy because I get to use the noble gas notation. Well, let's find gold right there. Okay, number 79. It's going to be 3, 4, 5D. Okay, it's going to be in the 5D. And so, but I get to use xenon to represent a whole lot of these inner shell electrons. I still have to represent some of the inner shell electrons, but here we go. So xenon. All right. So xenon says we're going to have, what is this? Here we go. So we think we'd have 6s2, 5d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you'd think, right? You would think that we would have, again, these two, this sublevel filled with 2 electrons going to be 6s2 and then 5d9. That makes total sense. However, remember, what we're actually dealing with is a situation which you'd think again it looks like this: 6s, my 1 orbital, up, down, and then I go to my 5d sublevel, which has 5 orbitals. You think up, 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 down, 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 right, to get to that 5d9. But here's the problem. Here's the weird thing that actually happens, especially when you get into the fourth period of the periodic table. It turns out that all of these orbitals, okay, in the 6s sublevel and the 5d sublevel, are actually very, very, very close to each other in like absolute energy. Okay, they're not separated by much, and it turns out that the repulsion that exists because of this single unpaired electron, okay, in relation to the 4 other orbitals that are doubly filled, completely filled, is actually greater than if this 6s sublevel were only half filled, but all 5 of these orbitals in the d sublevel were doubly filled. And so what happens is this electron right here actually jumps to this spot. Okay? I know it sounds wild, and it does seem like it can make this large, huge jump over there, but the issue is that you have to remember, the further you get down on the periodic table, the difference in energy between the different sublevels gets smaller and smaller and smaller. These different sublevels actually become closer and closer and closer in energy. And so this is actually not a large jump, because remember, all of these 5d orbitals are the exact same energy, right? So the energy of this orbital is not different from the energy in this orbital. And now you remember that the energy of this orbital is not much higher than the energy from this orbital. Okay, so conceptually, we want to understand that this jump is not actually that big of a jump. Okay, so even though it seems like it breaks rules, it doesn't actually break rules. There's just an interesting phenomenon. I even hate to say exception to the rule, because it's still satisfying the rules, just that things get kind of complex when you get further and further down the periodic table. So if I were to redraw this, okay, so what we actually observe with gold is a single filled 6s sublevel, and then everything else, every other orbital in the 5d sublevel is doubly filled. Okay? And the reason is there's actually less electrical repulsion from this one 6s orbital that's singly filled. because of the stability that's gained by 5 doubly filled 5d orbitals. Okay, so the stability that's achieved through this outweighs the instability that results from this. Okay, if that makes sense. We're weighing what results in greater stability. Like, that's the real issue. And so the reason this bears on the actual question is that I'm not going to write 5D 5D9 6S2. I'm going to write 5D9 6S1. Okay, it's a little tricky. It absolutely is. But as I mentioned before, the exception occurs when you're talking about elements in the group with chromium and the group with copper. So be on the lookout for these elements. These are the elements that make that exception. So be on the lookout. It's only those. It's only those. Okay, B. Identify the elements in the 6th period that have one unpaired electron in their 6s sublevel. So, 6th period. So 1, 2, 3, 4, 5, 6. Okay, so we're talking about this period. Okay, which elements have have one unpaired electron? One unpaired electron. So let's see. So obviously, when we fill the 6s1, okay, so cesium's going to be on there, right? Because that would just, the only electron being in this period would go into 6s1, so cesium. Okay, so there's one. Okay, what else in here? So this is going to happen where you actually see the 6s2 electron jumping to fill a d orbital. Okay, similar idea here. Okay, similar process. So the natural course of things is cesium. It's also going to happen with gold. Okay, like we just established, we've got that weird thing happening with gold. But also a little bit more difficult to predict, but it also happens with platinum, PT. Okay, but even though this is accurate, once you start getting into remembering this exception, you're getting on the scope of what you're trying to be taught in this level of course. Okay, some teacher at a high-level chemistry class might want you to remember that exception. They might want you to dive a little bit deeper into why that exception is in fact the case. But that's simply beyond the scope of this course. If you can remember, copper, silver, gold, and chromium as being this style of exception, you're doing really well.